Under the heading of elementary functions, we want to take a quick overview of power functions. Again, this is aimed at both pre-calculus students who are going to be learning this stuff and at pre-calculus students who've had pre-calculus and often don't know the difference between a power and exponential quadratic function, even though they can do considerable algebra, graphing, and manipulation with these functions. So we're trying to get the idea of the scheme, the overview of what the elementary functions are. We start by looking at power functions. So our basic power function is y equals x raised to the power p. Now, this function and associated functions, the functions that we can get by vertically stretching, if we think in terms of the graph of y equals x to the p, vertically stretching the graph or shifting the graph right or left or up or down, gives us a complete picture of the generalized power functions. Right now, let's just consider y equals x to the p. Okay, so that y equals x to the p has a graph that we could easily construct by choosing a value of p and plugging in values of x, making a table, and so forth. However, that's a very primitive way of constructing graphs. It's not appropriate to a pre-calculus course, except at the very beginning when we're trying to get a handle on some of these functions. So I don't want to do that at this point. What I want to do is I want to give you one of the characteristics of a power function. And it's a characteristic if your algebra skills are pretty good and you understand a little bit about what it means to prove things. And I don't assume that anybody, even having completed a pre-calculus course, really understands those things. But if you can, then we have a scheme for constructing graphs of power functions that's unified and very powerful. So the graph of y equals x to the p for any power function, for any value of p, has the property that if the value of x doubles, then the value of y changes by some specific factor. And I'm going to state that as follows. I'm going to say that doubling x always changes y by the same factor. For any given power function. I'm going to illustrate what I mean by this. So let's say that here is our y-axis and here's our x-axis in a right-handed Cartesian coordinate system. And I'm going to line off the x-axis in doublings. Now, the way I can do that, I can start with some small x value. I can double that x value, and I can make a mark on the x-axis at the point that corresponds to the doubling of that x value. I can then make another mark that corresponds to doubling this x value, which is of course going to move us twice as far from the origin, and we're going to be about here. I don't guarantee that I'm doing a good job of actually hitting the doublings, but you get the idea. So if I want to double this x value, I go out to here, and what I'm looking for is a point out here where this point is equidistant from here and here. I'll note that you could easily construct these doublings using a compass and a straight edge. Okay, and then I want to double this, so I want to come out here until I find the point that's halfway in here. halfway to the, I want to find the point such that this point is halfway to the origin. Okay, so there I have an x value in a series of 1, 2, 3, 4 successive doublings. Now, to get to the edge of the blackboard, how many more doublings would I need? I wouldn't need that many. Another doubling would put me about here. Another would put me about here. Another would put me out here someplace. So 3 more doublings would get me as far as I can go without leaving the edge of the board. So these doublings, of course, increase the x values very rapidly. Okay, now I want to go ahead and pick a y value, and I'm going to use a little bit of color here. There are those who don't think the use of color is appropriate in mathematics, and they have a point. So I'm going to pick an x value here, and I'm going to say that my factor for this function, let me write that out here, is going to be 1.5. Now we'll see what that means in a minute. This simply means a factor, of course, if something changes by a factor of 1.5, that means it gets 1.5 times as big. So if I change the x value by factor 1.5, it's going to get 1.5 times as big. I'm sorry, the y value. Okay, so the y value is going to change by a factor 1.5. So here's the y value. Now if the y value was to double, it would be here. I'm going to just make a little mark there just as an aid to illustration, but right here is halfway between the y value and the doubled y value, and that's the value we want. Now that value is going to correspond to the second x value, because here's the first x value, x doubles, and y increases by factor 1.5. That's going to give me a point here. Now I'm working in a pretty small area here, but it's going to get bigger. So here's my new y value. Now that y value, when x doubles to this next value, is going to have to increase by factor 1.5. So right here's my y value. If I double it, I think it goes to about here. And you can probably do this better and more accurately than I can, especially since I'm looking at the board at kind of a weird angle. But right there would be about 1.5 times this. So I can associate this y value with my next x value, and I get a point that goes about here. And I'm not all that sure of my vertical and horizontal alignment. I don't want to get in the way of the camera and block the board. I want you to see what I'm doing. And you understand that you can probably do this better than I can. So here's my x value. It's going to increase, or it's going to change by factor 1.5. This doesn't have to be an increase. The x value could change by a factor of 0.3. It means it'd get 0.3 times as big, 30% the value. Right now we're using a factor of 1.5. So here we go. Now if I double this, it puts me, I think, about here. And then halfway between here and here, I think, is about here. And I could refine this. I could compare these little marks and do all kinds of things and make this a lot more accurate, but I'll leave that to your creativity. Okay, so there's another x value. And we've got one more doubling here. So let's see. If we were to double this x value, we would end up about, here. And halfway between here and here is probably about here, and that would give us another point out here. So now we have these points. They don't lie along a straight line. There's a curvature to this. We can also reflect on the idea that every time we cut the x value in half, y is going to have to decrease by a factor of 1.5. Now, if you understand fractions, that means that it's going to become 2/3 as great. So every time x gets half as big, y becomes 2/3 as big. Now, x can keep becoming half as big as many times as you wish, so that y is going to become 2/3 as great as many times as you wish. with a little thought, it's at least plausible then that as x approaches 0, y has to approach 0. So I can conjecture that 0, 0 should be a point on my graph, and now the curve that seems to fit this graph looks something like this. Okay, so there is an instance where doubling x results in a change in y by a factor of 1.5. Now we could use any number we want here. We could use 2, we could use 4, we could use 8, we could use any number. And every time we do this, whatever number we use, the graph is going to be of a power function, y equals x to the p for some power. Now we do want to maybe think about how we could relate this factor to the power p. In other words, I've just constructed a graph. What's the power for that graph? What's the value of p that makes this the graph of y equals x to the p? What is the value of p? And also, how would we scale this graph? We don't have any numbers on this graph. What does that tell us? How would we determine what the numbers would have to be on this graph to make this y equals x to the p?